Executive summary. The term Intel architecture encompasses a combination of microprocessors and supporting hardware that creates the building blocks for a variety of computing systems. Although the architecture is straightforward and remarkably well supported, the workings of these components may not be obvious to engineers, programmers, or product developers with no previous Intel architecture experience. This paper describes the basic operations and functions of the relevant components using 3 example systems. Specifically, the paper will focus on the Intel Core i7 processor high performance and the Intel Atom processor low power implementations. In each case, the paper will walk the reader through the operation of the microprocessors, communication with memory and peripheral input-output devices, the interaction between different types of components and related design criteria. The various system components are described along with the services they provide. This paper will also define common terms. The final section highlights design, aids, support, and collateral provided by Intel and its partner provides to help create successful products. The goal of this paper is to describe the basic operation and function and 3 classes of hardware platforms based on the Intel architecture and the components used. White paper introduction to Intel architecture. Table of contents. What is Intel architecture? Introduction to Intel architecture. Basics of Intel architecture system. Intel Core i7 processor based system. The Intel Core i7 processor. Intel's Direct Media Interface DMI Platform Controller Hub. PCH Intel Atom processor based system. The Intel Atom processor tools for new designs. Conclusion and references. What is Intel architecture? Intel is the world's oldest and most established microprocessor company, producing the world's most popular microchips. Although perhaps best known for its PC processors, Intel devices are used in virtually every field of electronics, including automotive, industrial automation, robotics, consumer electronics, image processing, networking, encryption, military, construction, medical, energy, and other industries. Designers unfamiliar with Intel architecture may have concerns about the architecture's fundamental concepts, its inner workings, or its complexity. The goal of this paper is to educate skilled developers with no previous exposure to the Intel architecture and to provide guidance regarding system components and concepts. Introduction to Intel architecture. Since the first tiny Intel 4004 microprocessor chip was made in 1971, Intel has produced an unbroken series of upgrades and improvements to the world's best-known microprocessor family. From its early 8-bit beginnings, the Intel architecture now encompasses a range of a 32-bit and a 64-bit microprocessors that address a range of applications, performance requirements, power levels, and price points. The cornerstone of Intel's architecture's popularity is its compatibility. Each new generation of Intel's architecture microprocessor is a superset of its predecessors, providing backward compatibility with all the chips and all the software, while also adding new or enhanced features. This compatibility allows engineers, programmers, and development teams to reuse the software and software development tools from earlier projects, protecting their investment in time and talent. It also makes developing new Intel-based systems easier by leveraging developers' experience. Software can be reused across generations of products, and product teams can protect their investment in both hardware and software in a cost-efficient manner. Although original work may be required to take advantage of the newest microprocessor features, the old software will still work as is. Intel architecture chips have obviously undergone many changes over the past 40 plus years. A list of currently available devices is available here. Early chips were given technical part numbers, such as 8086, 80,386, or 80,486. This led to the commonly used shorthand of x86 architecture in reference to the last two digits of each chip's part number. Beginning in 1993, the x86 naming convention gave way to more memorable and pronounceable product names, such as Intel Pentium processor, Intel Celeron processor, Intel Core processor, and Intel Atom processor. Although every branch of the broad Intel architecture or x86 family tree retains the same basic features and functionality as the earlier chips and retains backward compatibility with them, each new generation also adds its own unique feature to the mix. For example, Intel Pentium processor added multimedia extensions called MMX technology that accelerated audio and video processing. External temperature Intel Pentium processor with MMX technology is with the most streaming media capabilities, known as Intel Streaming SIMD extensions. Intel SSE and Intel Streaming SIMD extensions to Intel SSE 2 floating point units FPUs went from optional upgrade to standard feature of Intel architecture processors, and today encryption to decryption extensions. Power management features and multi-level caches are now found on most Intel architecture processors. Data paths have widened from 8 bits to 32 bits, 64 bits, and even 128 bits and more. Operating frequencies have jumped from a few megahertz to 2 gigahertz, 2 billion cycles per second and beyond. Some abbreviations used in the diagrams below: BIOS, Basic Input Output System, a boot ROM, read-only memory; DDR3, double data rate, version 3, a popular DRAM interface standard; DMI, direct memory interface, video graphics standard; FIVR, fully integrated voltage regulator; LPC, low pin count, a simple interface to slow input-output devices; PCH, platform controller hub, a companion chip; PCI, peripheral component interconnect and popular expansion bus; PCIe, PCI Express, an upgraded PCI standard; SATA, serial ATA, popular disk interface standard; SPI, serial peripheral interface, simple interface to slower devices. Alhamdulillah. PCIe Gen 3.0 with 16 lanes with up to 3 controllers. DisplayPort eDP/DP 1.2 DVI HDMI asterisk 1.4a 4th generation Intel Core or Intel Pentium processor. DDR3/DDR3L 1600 1.5 volts dual channel eCC optional SKU dependent fully integrated voltage regulated FIVR. DMI Intel flexible display interface Intel FDI. Analog VGI Intel high definition audio 6 to 8 PCIe times 1 Gen 2.0. Intel Ethernet connection I200 17 LM I200 18 LM. Intel H881 Express chipset or Intel Q87/C226 chipset. BIOS support 4 to 6 SATA ports, 2 to 4 SATA 6.0 gigabits per second, 14 total USB ports, 4 to 6 USB 3. Figure 1, typical system, that's what we were just reading. Figure 1, typical system based on the Intel Core i7 processor White Paper, Introduction to Intel Architecture. DDR3L memory down SO-DIMM. Up to 2 channels configurable as 1 channel with eCC. Up to 2 ranks per channel. 2 times SATA Gen 2. 3 times high speed USB 2.0. 1 times high speed USB 3.0. 2 times USB 2.0 HSIC. 1 times eMMC. 1 times SD card. 1 times SD10. Intel Atom Processor E3800 product family. 4 times PCI Express Gen 2.0. DisplayPort EDP HDMI VGA. Intel High Definition Audio. Low Power Audio. SIO. Figure 2. That was Figure 2. A typical system with Intel Atom Processor SoC. Similarly, many Intel architecture chips now boost multi-core performance, meaning that 2 or more Intel architecture processor cores or engines operate within a single chip. Many also offer multi-threading, a technique that is designed to improve performance by allowing a single Intel architecture core to perform multiple tasks. All the while, the power consumption and heat dissipation of these processor chips has been kept in check thanks to aggressive on-chip power management hardware, some of which is adjustable through software, and industry-leading semiconductor manufacturing technology. An in-depth description of the Intel architecture. Technical features can be found in the Intel Software Developers Manual, available here. While the processors have gotten even more capable, there have been similar advances with the support logic, the development tools, and completely integrated hardware platforms. Every Intel architecture processor is supported by one or more chip sets that provide needed system-level functions, and some Intel architecture processors include their own integrated functions, such as memory controllers, graphics engines, or network interfaces. Sometimes the chipset is internal, and the processor becomes a standalone SoC, a system on chip. Basics of an Intel architecture system. The hardware requirements for each customer application will be different, of course, but some basics apply to all. The processor chip itself is just the beginning, with few exceptions. The processor does not stand alone, but works in concert with compatible support chips. Different Intel architecture processors work with different support chips, and this paper outlines 2 representative examples. The first example describes a typical hardware platform based on the high-performance Intel Core i7 processor, combined with similar high-performance support logic. See Figure 1. The second example focuses on small, low-cost Intel Atom processor-based systems. See Figure 2. Generally speaking, every Intel architecture hardware platform will include 2 major components: the microprocessor chip and a companion chip known as the platform controller hub, PCH. In earlier times, Intel processors were paired with 2 companion chips, often called the North Bridge and the South Bridge, or the MCH and the ICH. Nowadays, the functions of the North Bridge are usually included in the processor itself, while the South Bridge has been replaced by the much more capable PCH and single chip SoC configurations. There is no PCH, its functions are included in the processor itself. Surrounding these 2 components, meaning processor and PCH, will be other customer supplied components including DRAM, boot ROM, a power supply, and the peripheral interfaces appropriate for the system, such as a network or sensor connections. Most systems will also include some non-volatile memory, meaning flash, or E2P ROM, and perhaps some glue logic that is specific to the application. As these diagrams show, one of the example systems is based on a two-chipset processor and PCH, while the second example uses only a single chip, the processor, with integrated controllers. The former is designed for higher performance and more expansion capability, while the latter is optimized for small size and low cost. These examples highlight just two of the many options available to designers of Intel architecture systems. Intel Core i7 processor-based system. The example in Figure 1 illustrates a high-performance system based on the quad-core Intel Core i7 processor, the Intel Q87 chipset, Intel DHA2 Q87 PCH, two banks of external DDR3 DRAM, and several peripheral devices and interfaces. This configuration represents a high-end system with maximum performance, with the maximum capability of expandability. The Intel Core i7 processor, the heart of this system, designed as the Intel Core i7-4770S processor, a high-end 64-bit implementation of the Intel architecture. The particular fourth generation or Haswell Intel Core i7 processor shown in the diagram has several notable features, including 4 independent CPU cores, two-way multi-threading per CPU core, a built-in two-channel DDR3 DRAM controller, integrated L1, L2, and L3 caches, direct media interface DMI connection between the processor and the PCH. The Intel Core i7 processor achieves its high performance through its multiple CPU cores and its simultaneous multi-threading SMT feature. Between the 4 cores in this example and the two-way multi-threading core, the Intel Core i7 processor appears to serve as 8 independent 64-bit CPUs. Figure 3 shows a representation of the silicon die for Intel Core i7 processor with its 4 independent CPU cores and other features highlighted. Figure 4 shows a conceptual diagram of the same processor, illustrating how the 4 CPUs each has its own L1 and L2 caches and a shared L3 cache. The processor's on-chip DRAM controller is responsible for cache coherence. If data at the address requested is not in one of the processor's caches, or if the data in external memory is newer than the cached copy, the memory controller is told to retrieve the data at the requested address. Data transfers between the processor and memory are always 64 bits wide, the full width of the L2 cache on the processor. If only a byte of data is requested, the full 64 bits are retrieved, but the processor may use only 8 of those bits. The memory controller is configurable via the BIOS support to support multiple speeds and or sizes of memory. DRAM refresh is also handled by the memory controller after it's initially configured. The specific type, size, and speed of memory supported varies by processor. The PCI Express PCIe interface is the highest bandwidth input-output interface in the Intel architecture system. The number of PCIe lanes can vary depending on the processor used, but will usually be n. multiples of 4. Common width for PCIe is 16 lanes, as this is the maximum width for discrete PCIe graphics cards. The PCIe interface uses the same differential signaling as the DMI, although PCIe supports higher transfer rates. The original PCIe specification specifies data rates of 2.5 GT per second, 250 megabits per second per lane. I'm feeling kinda tired. We'll continue later. And with Intel's Direct Media Interface, DMI.